So welcome to the security room, and I'll give you the first talk about software supply chain security, especially in the context of infrastructure management tools. So I'll just start by introducing myself quickly. So I have a sysadmin background, and I'm currently lead system developer at Rudder. And I'm also a member of the Secure Code working group of the Rust language project. So I will try to give you both points of view from a software editor selling software to end users, and from an ecosystem programming language point of view, which are quite different but complementary. So this working group works on the vulnerability database for Rust programs, and also does some security-related tooling for the Rust ecosystem. So I will start by talking a bit about infra management specificities. So they tend to run ubiquitously, almost everywhere, whether with an agent or a remote connection. They usually have high privileges, often admin privileges, and they often act as a glue between different systems, which means they interact with a lot of different moving pieces. And they are actually quite complex software, comparing to other remote access stuff like OpenSSH or other systems. And this means that they have a lot of different components with a big attack surface and a lot of dependencies, and we'll talk about this more. So all of this makes infra management software good targets for attacks in general. So we know about vulnerabilities directly in the infra management software that happened in the past and will continue to happen in the future. But we're not here to talk about these, but more about what happens upstream, and what other kind of security issues we might have, not directly linked to bugs we write in infra management software code, but somewhere else in the stack. So where does infra software come from? Well, it actually comes from a software supply chain, which is made of sources, which are then at the end delivered to the client, either through software as a service or on-premise stuff. And we'll see each part of this chain and how they can have security implications and what we can do about it. So it all starts with a developer who writes code. So this is the first part. So he's working on the infra management project or for the company. He has a workstation with a lot of privileges, and that's maybe the first vulnerability here. And he has a lot of accesses to a lot of systems. And it's often underestimated, but it actually causes a lot of problem. And the recent Circle CI breach, for example, was caused by a compromised engineer system, which gave access to a cookie with high privileges, and then led to the compromise of the system. But it's a bit out of scope for today, so we'll skip this one. As we are working on quite complex projects and with advanced needs, we often need to have dependencies in our codes. We won't write everything by ourselves. So whatever the language we're using, we will use dependencies. So that means that in addition to the code we write, we will import in a way or another a lot of other components, usually open source components, whether it's for an open source infra software or even a closed source infra software. Or today, almost all big software projects have open source dependencies, and a lot of them, from various ecosystems, so it depends on the programming language. But to sum things up, the dependencies add a lot of developers to your project, basically. Even if you write it alone, that's like you have tens or hundreds of people writing code that end up in your product. So what does that mean? That means that a lot of people have kind of an indirect access to your sources, because if you update your dependencies, then you're fetching code from an unknown amount of people that you don't know, and you don't know anything about them. So this kind of gives them write access to your code, and that can be a problem. Because you can't really audit all dependencies. Very often you have an amount of dependencies that mean you may audit it the first time you import it, but when you update one of your dependencies, you probably won't review all the code all the time. In most cases, it's practically impossible. So it can only be a heuristic or a community effort. And this has the current tendency is that the number of dependencies is constantly growing, and even outside of pathological cases like NPM JavaScript stuff, which has thousands easily of dependencies, it's also the case with other ecosystems. So this is not going to disappear. This is going to become worse. Just to give you a quick estimate, I took one of the daemons we have in Rudder, which is written in Rust, and I ran the cargo supply chain command on it, which is a command that scans all dependencies for the list of people who have release access on these dependencies. And I found that for this particular program, which is kind of critical as it handles the communication between nodes and servers, we have 140 individuals with release access to these dependencies and 34 GitHub teams of people we generally don't know anything about. And we basically trust them. And we're not alone in this, and basically all complex programs nowadays have this kind of structure with a code written by the program developer themselves and a lot of dependencies from unknown people. So the attacks on the dependencies have increased in recent years because it has a huge potential, as you can see. You may have heard of Log4Shell, for example, which was an RC in a popular JavaScript logging library. And this really showed that not a lot of organizations really know what is running in their companies, and a lot of admin teams were a bit in panic to find out where there could be a copy of Log4j running. And it shows that the software stacks are really deep now, and people generally don't have enough visibility to keep track of the security risks. So just to give you a simple example of how easy it can be to compromise a dependency used by a lot of people, that's something that happened on EventStream, a popular NPM package with more than 1K stars on GitHub. And one release was published including code to steal crypto ledgers on developer computers. And when contributors tried to find out why it could happen, then they asked the maintainer, and the maintainer basically said that someone sent him an email asking for publish rights, and so he gave it to him because he didn't care about the library anymore. So it shows you how easy it can be to compromise a software stack with hundreds or thousands of dependencies. Maybe just ask. On the Rust side, it also happens, even if it's a smaller ecosystem with less dependencies in general and a younger ecosystem. There have already been typo squatting attacks. So typo squatting is when you publish a library with a name close to a popular library, and you expect that some developers will, for example, miss the underscore, and they will get an almost identical library, but with an additional payload. And in this case, it was an attack against GitLab CI with a specific code to attack GitLab CI where the code could be tested from. So what do we learn from this? The good news is that people are generally nice to each other because we rely on hundreds of open source developers that, on average, are professional and nice to each other. So that's good news. The bad news is that that's basically our only protection now. We don't have much more to protect from these. So we see the rest of the supply chain now. So the developer will push code to a repository. Repositories can be attacked, but it's probably not the easiest channel. But well, you need to keep track of deploy keys and SSH keys and everything. You can also use some features of the development platforms, like protected branches, to prevent some unwanted accesses to your repositories. Okay, so now let's continue to the next step, which is a very important one, which is the build. So what does it mean? Well, we'll generally set up kind of a build environment. Can be containers, VMs, can be running on software as a service like GitHub Actions or Circle CI, can be a hosted Jenkins or anything. It will download all sources, including yours and all your dependencies. It will build and probably push something somewhere. And it's actually a really important step, and one that has really a growing attention now. And for example, the SolarWinds attack, which was well known, but the details are not as known as the effects. And actually, the SolarWinds compromise was done on the CI platform with attackers that gained access to a persistent build machine, and they had a script running every second, checking if there was a build ongoing. And if it detected a build command, it would find the path of the build command and edit the software on the fly before it is compiled to add the payload. So that's a really effective attack, because you are then using the normal update channels, and customers will all download their signed updates as if nothing was different. And they even took extra care to make the CI happy. So they added pragmas to remove warnings in the payload, and they ensured that it was actually the good version of the code. So they really took extra care to make the CI green so that it stays undetected. We have a lot of other attacks against the IaaS platforms, either hosted or software as a service. So what we can learn from this is that build environments are actually critical assets, and they really need to be treated as such, and it's not always the case. That we need to do security monitoring and security fixes on the build platforms too, because they are a critical aspect of the software security. And we need to ensure we download the right sources, so that means including log files and signatures check on the download part of the build process, so that you ensure you are only downloading what you want. So then we have built software. We'll push it to some distribution or maybe production in case we deploy the software ourselves. It's the step that is in general not the worst, and we have standards like Linux package manager, for example, or other means that usually include some kind of signature check. So that's probably the best part of the supply chain currently. That's something that's been addressed for quite some time now. So I won't focus on it much more. And now we end up with the end of the chain, and we end up on the end user side. And now we will see in this whole chain, and given all these risks, what do end user actually need to help them stay secure for their own business. So the first thing that they need, and that a lot of things showed us, like the Log4Shell case, was that they need visibility. The first thing is that they need to know at least what is inside the software they run, what are the components, which versions, so that they can monitor known vulnerabilities and know if they are affected and act effectively. So that's the first need that they have. And the second one is a matter of trust, because the software editor can always give a list, but how will the end user be able to be sure it's actually what's included in the software? It can very easily be an updated list or something manually updated, we don't know. So there's also this big trust issue for end users about information they're given about the software. So an integrity problem, actually. How can we reach these goals to help end users? So before starting to explore the solution space, I'll talk a bit about the OpenSSF, so Open Source Security Foundation. It's affiliated with the Linux Foundation. It was created last year, so it's really recent, and it merged, actually merged several previous efforts for mostly supply chain security, and we will see that a lot of projects are actually linked to this foundation. So how to address the visibility problem? So we want to give the users a list of the components with their versions. The first problem is that actually identifying software is a hard problem, and it's becoming harder and harder. We are used traditionally to CVEs, including a CPE identifier. CPE is just not working for current needs, with a lot of software repositories for each language. It just doesn't work, and you will have a lot of false positives if you try to scan software libraries using CVEs, because CPE are not enough to identify stuff correctly in the current, in the correct context, with the correct version comparison algorithm and everything. So it basically doesn't work. So there are new ways of identifying software. So I'll talk about two of them, software ID and PURL. So PURL is a uniform identifier, like a URL, but for software. And it's especially made for upstream stuff, like package managers and programming languages, package managers, and this kind of stuff. So they work like this. So you have the context we are talking about. Is this a Docker container? Is this a Go package? Is this a Rust package? Then the name, the version, or maybe a commit number. So the idea is to have a precise description of the software and its version. And it's really important because we'll see that it's hard to keep track of all the components, so we need very precise description. Software ID is better for more aggregated or downstream stuff. So it's made by the NIST, and it's usable in CVEs, but not used that much for now. It looks like this, so XML, like a lot of historical security-related stuff in SCAP. And it's mostly useful for more downstream stuff, so end-user programs, software, operating systems, and so on. So now that we have a way of identifying the software precisely, we have a problem of being able to list the software we have. And what will this software library list be called? Well, it's actually usually called a software bill of materials, SBOM. It's basically the list of ingredients that make the software. And we'll talk of a few of them and how we can use them. So the first one to appear in the open source ecosystem was SPDX, which started around 13 years ago. But the first focus was on license compliance. So it's more license oriented and has moved towards security needs more recently. But that's probably the ones that's most used for now, and it also included all the standardization around the licenses, license identifiers, and all this stuff. So that's also made by the Linux Foundation. And there's also Cyclone DX, which was made by OWASP, which is more recent, 5 years ago. And this one is really more security oriented. It has been thought for it from the beginning, so it goes beyond the whole Cyclone DX project goes beyond simple software bill of materials, as it also includes more general stuff like hardware bill of materials, operations bill of materials, and so on, to describe more broadly the context in which the software was built. Because knowing the list of software is good, but knowing the context it was built may also be important. So that's additional information that can be important. And Cyclone DX also includes vulnerability management stuff. So VDR, VEX for vulnerability disclosure report and vulnerability exploitability exchange, which are formats to describe how you can report a list of vulnerabilities against a program and how you handle these vulnerabilities. For example, in VEX, you can describe that this specific vulnerability can be ignored in your organization because of this reason. And that's a structured format to describe this, which is currently usually done in an ad hoc way. And the idea is to make it more structured because the volume is always increasing. So we have seen that we can have software bill of materials, which include the list of software and versions and maybe a bit more about the context the software was built. But we also have a second problem, which is to be able to track the vulnerabilities in these components. So historically, the way we track vulnerabilities and we talk about vulnerabilities is through CVEs. So that's the historical tool for this. But as we seen with the software identification, the old tools are not enough for the current needs, and especially the multiplication of software sources and the amount of libraries that we use in programs. So there have been several initiatives in this regard. So I'll talk about one of them, which is OSV, for open source vulnerability. It was originally created by Google. The idea is to provide a format and a database, but the format tries to match the needs of programming languages needs. So keeping track of npm, maven, and Go dependencies vulnerabilities, because CVEs were really not good at this for two reasons. Because it's hard to identify if we are talking about a Go library or an npm library with the same name, and if they have matching versions, then CVEs become basically hell. And we have one of our vulnerability checking tools which runs against CVEs, and we always have false positives, like a Chrome extension with the same name than a Java library we use, and it reports a CVE on this, and we're like, no, that's not for us. So there's also a scoring problem, because CVE score is made for end users, but libraries are really upstream, so the score is not adapted to libraries vulnerabilities, because we don't know how it's used. So depending on how it's used, then almost any library vulnerability or even bug could become a critical vulnerability in the end user software. So we either rate everything very high, or we don't know. And currently, that's a problem we have in the Rust secure code working group. And we originally included a CVE field in the vulnerability description format, and we ended up reconsidering it because it's often quite meaningless, actually, except in some very cases where we know it's a security problem, if it's an authentication library or something. But if it's like a data structure library, a general data structure library, then maybe it's critical in the program that use it, if they use it for user authentication, and maybe not. And it's really hard to give good insight about this. So it contains a specification which uses the PURL format for identifying software, which allows correctly identifying software. It also stores the algorithm to use to compare versions. So it may be semver, it may be something else. And CVEs absolutely don't have this kind of subtlety, but that's important, and especially for, let's say, pre-version numbers and software identified by a Git commit, or there are a lot of corner cases around versions that are only addressed correctly by this kind of formats. It's also extendable, and for example, one thing that is currently growing and that will probably become more present in the future is the ability to identify in the library which function or interface or object is affected by the vulnerability. Because once you start putting vulnerability monitoring on your dependencies, you will end up with a lot of reports, and actually a lot of false positives, because you often don't use all of the library's features. There is currently work in several ecosystems to try to make the alerts better by specifically targeting the parts of the libraries that are affected. So at ecosystem level, we basically have one vulnerability database for each language. So Go has its own vulnerability database, NPM has a vulnerability database, Maven has one, Rust has one, and they are almost all aggregated in the OSV database. So along with the format, there is also a common database hosted by Google that has that aggregates all the vulnerabilities in the OSV format, and that's really important because that allows auditing software to have a consistent view of the vulnerabilities across different ecosystems, and so you can have generic tooling around this. There are also been efforts at GitHub to handle software vulnerabilities. So they have their own database, which are the GitHub security advisories, and you have a whole set of features in GitHub to report vulnerabilities and detect them and open pull requests when you have a vulnerability in a software. So I think this really helped people to become aware of the problem and to help to get aware of the problem, but it's also not a complete solution, as it only addresses stuff that is hosted on GitHub, which is good for Microsoft, but maybe not for the whole ecosystem, and it tends to give a kind of a monoculture around GitHub, and it's maybe not something we want. That's a bit of a problem. And there's also the problem that the GitHub security advisory database is not always synchronized with everything, so you end up having to choose which database to use, and that's a bit of a problem. I think it will become clearer after time, but for now it's a bit complicated. Okay, so that was the visibility topic. So we saw that we can list software in software bill of materials. We saw that we can get visibility of the vulnerabilities. So with this OSV format, you are able to audit a program for vulnerabilities affecting its dependencies, and you can get a report about this. So that's already something. You could either audit the sources, or the software bill of material. That's also an option, which allows end users audit their programs even without the sources. But that also leaves open the question of how can we trust this information, and how can we trust that the program we have is actually the one we want. And for example, in the SolarWind case, let's imagine we had a software bill of materials. Then it would be wrong in the case where it was compromised, because one of the sources was not actually what it was supposed to come from. So we need a way to make sure of what we're manipulating, and we need to have this integrity notion across the whole chain. So it starts from the sources. We need to be sure we are building from the right sources. We want to be sure that we are building in a safe build environment and with specific tooling versions without vulnerabilities and so on. And we want to sign the artifacts and what we will deploy afterwards. So signing an RPM package is good, but it's absolutely not enough for the current needs. So there are several ways to address this. One of the most popular is using Sigstore. I won't go into further details because there's a talk just afterwards about it. So I'll let you attend the next talk for more details. But the idea is to be able to sign and verify signatures across independently from what the vendor claims, basically. So what can we do now that we see we have a lot of things to address? Well, we now have some tooling. That's the good news, is that we now have some tooling. We heard about these supply chain problems for years, maybe 10 years, but until now, the tooling and the ecosystem was really too young to be able to actually be efficient in fixing the problems. But since 1 or 2 years, maybe, things are really going faster, and we now have usable stuff that we can start to work on. So the problems that we have is that this problem space is actually huge. We have thousands of dependencies. We have very complex build platforms across cloud, software as a service stuff, and we deploy it on a whole lot of different places. So it seems like too much. We can't review everything. We can't audit everything. So it may be a bit, it may seem a bit too big, but and also the cost is huge if you want to check everything. So you can't check everything. You can't be sure. That's mostly a risk management problem and not an exhaustive check problem. And so you need to prioritize and focus on the important parts. You can't just do everything. So I'll talk a bit about SLSA, so it's pronounced SLSA, for supply chain levels for software artifacts. That's actually originally from Google, now under the OpenSSF, Open Software Source Foundation. And it provides basically checklists and levels that allows you to identify where you are in terms of supply chain security. So that allows prioritizing important stuff and then moving towards more security. So the goal is to help list the problems and fix them in the right order. It's not transitive, so that's a really important thing about SLSA, is that you may have the level of each component in the chain is independent. So you may work on your own software and make it, give it a high level. We'll see the levels just after. Give it a high level, even if you include dependencies with absolutely no compliance to SLSA. The idea is that well, that's always the same. It's impossible to have a full ecosystem, so compliant with SLSA. So you need to start somewhere, and the idea is to get going on this, so it doesn't require transitivity, which would make it totally useless, actually. So how does it work? You actually have 4 levels, and for each level, you have a list of items that need to be checked. So I took just a part of it about sources and builds. So, for example, for the first level, you need to have a fully automated build. So if you have some build steps or release steps that are manual that run on one of the developer's machine, then you don't have the SLSA 1 level. So you need to automate everything, and you need to use a build service. So that means it cannot run on a laptop, basically. And then for level 3, everything should be described as code and in an ephemeral environment. So that gives you a list of items, and the good thing is that it allows you to prioritize things. And given the huge amount of problems, basically, it gives you a starting point. So you can go for SLSA level 1, and what do I start with? So level 1 is basically the visibility aspect. So the idea is to be able to know what you are building, where you are building it, and how you are building it. So you want to have a full automation of the build and a list of including software and the description of the build environments as precise as possible. So for example, which Docker version are you using, and we want to be able to, which Docker container version you're using, and you want to be able to really describe precisely how the software was made. So it gives the visibility, but it gives no integrity properties. It's just the visibility, but that's already something really important, and that's not always fully covered by current build systems. And it allows the end user, once they have this information, to make decisions based on the actual risk that they have. But it includes, as I said, no protection against tampering or anything. It's mostly declarative. And then the other 3 levels are increasing levels of integrity and validation of the process. So level 2 has a first level of provenance, which are basically certificates that attest a specific state of the system. And then you have growing levels, level 3, level 4. And the idea at the end is to have a 2-person review of everything that changes enforced, and a completely reproducible and hermetic build process. So that's the goal that is not easy to attain, and if you list all the items you have to check, that's really the end goal, which is still far for most software editors. So where are we at now in this regard? So I'll talk a bit about Rudder and how we have started working on these topics, and also what we want to do in the future. The first problem that we have in this regard is that we have a lot of ecosystems. Rudder has different agents, has more than 10 years of history. So we have a lot of software, especially programming languages ecosystems. We have some Scala stuff in the backend, so Maven based. We also, for the front end, have some Elm and JavaScript stuff, so 2 languages for the front end. We have some Rust for system services. We have some F# on Windows. We have some C dependencies that we embed in our agent. And we have some Perl and Python for some glue at some points. So that makes a lot of different ecosystems. And when we build a release of Rudder, we actually pull things from all these sources, these kind of sources. So that makes it really hard to keep track of everything. So the first thing that we had to do was actually we focused on the vulnerability scanning problem, because that was our first priority. We wanted to know if there was a known vulnerability in one of our dependencies in one of these languages. And that wasn't easy because the tooling is really getting ready, but not always complete. And it required a bit of glue to get everything working together. But now we have this in place. For the software bill of materials, we are not there yet. We basically have a list for each ecosystem in text or JSON or something, but we don't have, for now, the aggregated view of all the ecosystems in a single SPDX or CycloneDX format. That's still a bit complex. We could do it with some of it, but, well, partial software bill of materials is not that useful. So, yes, for now it's not done. It will probably come in the next months because the ecosystem is really moving fast, and things are changing really fast, and it's becoming possible. So vulnerability scanning is in place. We actually do it daily, so we have a daily CI jobs that will scan all our dependencies for non-vulnerabilities using dedicated tooling for each ecosystem, which gives a lot of special cases to handle and a lot of jokes, like the F# tooling that always returns 0 even if it finds a vulnerability. So you have to grab for the output to check if there is something, and there is a lot of small things, but getting it all together was not easy, because there is nothing very consistent for now. For the integrity stuff, we basically don't have anything for now. We don't use Sixtor. We just sign our packages and that's all. So that's still something that we have to work on. We worked quite a lot on the build process security and reproducibility. We still had some persistent builders, which we got rid of almost entirely, and we now build in ephemeral build environments, which also helps describing precisely the build environment, because as you recreate it every time, you have a precise list of what you install in it, and we specify the exact versions of all the build dependencies. The funny thing is that you also have to scan all those build dependencies for vulnerabilities, because if you have a vulnerability in one of your compilers, then it's affecting your whole software. So you need to also keep track of everything that affects the build platform. So the next step for us will be to aggregate the software bill of materials and continue making the build infrastructure more deterministic. It's still not fully reproducible or deterministic. And now I'll talk more on the ecosystem point of view in the Rust project about the current situation. So vulnerability tracking is okay-ish. We have a database. We have basic tooling to audit program sources for non-vulnerabilities. They are transformed to OSV format and sent to the OSV database, which gives access to other tooling like software bill of materials tooling or vulnerability checking tooling that I will talk a bit about later to scan for non-vulnerabilities. The software bill of materials is getting ready. There are some early versions of tooling for this. It's still very young, but should becoming to work. We also have a project from the work group that embeds the list of dependencies inside the binaries. So that allows easier tracking of especially vulnerabilities, but also allows making a software bill of materials and checking them. There is still a lot to do on the package server, so the equivalent of npm for Rust, which is crates.io. the security features are not all in place now. We are still missing some second-factor authentication for publishing software. We are missing some ways to identify the vulnerabilities in an easier way from the site. So there is still quite a lot of work in this regard. There's a last point I want to talk about. It's how we handle the amount of dependencies. That's a critique that's often made, for example, of Rust. For example, compared to C or C++, where you tend to have a lot fewer dependencies. I'm not sure it's for good reasons. I think the biggest reason for the low amount of dependencies in C and C++ is that it's really hard to do, and composing C code and building dependencies is really hard. Whether with Rust and the cargo build system, it's quite easy. So this it's easy, so people tend to use more dependencies. And the easier it is, the more dependencies are used. And I don't think the solution to this is to just make it really hard to add dependencies so that people don't have too many of them. So there have been a few projects trying to explore what we can do to actually validate and audit the dependencies, because we can't do it ourselves, but maybe as a community we can help each other and audit a bit of the whole ecosystem and rely on audits from other people. So there have been two initiatives, Cargo Crev and Cargo Vet, with different approaches, but the idea is that basically you can make some audits of specific versions of specific dependencies, and you can also collect audits from trusted parties, trusted third parties, and so you can have more trust in what you are importing without auditing everything yourself. So I will now conclude. So all these supply chain security efforts are mostly driven by enterprise and government needs, especially the US government after the SolarWinds issue. So one of the consequences is that it tends to lead to quite complex solutions. It's a bit top-down, so it starts with a 600 pages PDF from the NIST, and then you try to find ways to implement this in open source ecosystems, and that leads to stuff that is not that easy to implement. Another problem that I found is that there are far too many acronyms in this domain. It is terrible. I don't know if it's because of the enterprise or government stuff or because the security people are more inclined towards acronyms, but I really spared a lot. There are way too many acronyms. The ecosystem is in general quite immature. The norms are still not really accepted everywhere. There are still some competition between tooling and formats and everything, but I think it will settle down pretty quickly. We are now in a very important time. Things started to accelerate a few months ago, and I think in maybe 6 months or 1 year it will be way clearer. But for now, it's changing continuously. So if there's one thing you should remember from this talk, is that even if it's not easy, we can't just ignore the problem, and we need to take action on it. At all levels, whether open source ecosystems, software editors, or end users, especially as a lot of us, even if not software editors, are actually kind of software editors, because if you write a Python script and you pull 1 or 2 dependencies, you put it in production, then you are a software editor, and you have basically the same responsibilities than a company that would sell software. And you have the same risks, actually. So I give you a few references for more information, because that's quite a broad topic. So the OpenSSF with SLSA, OSV, Sigstore, the OWASP Foundation with CycloneDX, pbomb.dev, which is really new. It appeared like last week, I think, with OSCAR, which is kind of the the Mitra attack framework, describing all the possible ways you can attack the software supply chain. That's a kind of a reference, a list of potential issues. And also a few companies, ChainGuard, which is working a lot on the SIG-Store and signature stuff, Aqua Security with some open source tooling like Tri-V, and Core with Gripe, Sift, which are vulnerability auditing and software bill of materials tooling, also open source. Omnivore, which tries to embed a precise list of which dependency is included in which artifact. The goal is to make less false positives by having a precise relationship between the sources and the produced artifacts. And I think that's all. Do you have some questions? Yes? Mm-hmm.
Just download the Docker. What's in the Docker? Just download it. Yeah, what's in it?
Yeah.
Just download it. And so we've got all of these black boxes. All of these. Please run this script as good and don't ask what's going on.
Yeah.
Yes.
Yes.
And there's no vetting going on there to make sure that someone's not
Sure.
made the type.
Sure. Mm.
So we've not solved the distribution problem at all.
We
solved it and then made
yeah.
difficult and
Yeah.
created faults.
We have working tooling, but it's not always convenient enough for developers, so they just do it another way. Yes, that's also a problem. That's true. Yeah. Good remark. Yes?
I don't know anything about security, but as a dev, I get a lot of people running vulnerability scanners using replay, especially in the last year, and raising loads and loads of issues about CVs, which I then have to respond to. So often the CVs are on a dependency that I use, but I'm not actually using any of the vulnerable functionality. So you mentioned OSV has some sort of idea about seeing which functions inside the dependency actually being used. But I don't see how you can identify those functions using file or SWID, because those things are individual.
It's not possible. This requires ecosystem-specific programs, and depending on the ecosystem, it may be easy or almost impossible. So that's really something that is ecosystem-specific. But I know for Rust, we currently store the list of functions, but don't use it in the audit because that's too hard for now. So that's a project, and I know some ecosystems might be a bit better in this regard. Maybe Python, I'm not sure, but I've read some stuff around it. So that's an idea that is floating around, but currently in the implementations, it's not done yet. Yes? I think that could be of great use because they have a lot of the properties we want built in into the system. But the problem is that the current build systems are far from it, and the migration cost may be prohibitive in some cases. But if you have a Nix build system, that's obviously a great step, and you have a lot of work already done. Yes? Some package managers include, so for example, npm by default will check for vulnerabilities at build step. Yeah, it's mostly reactive. For what I know, that's mostly reactive. I'm not aware of a lot of initiatives for there are some, but most of the tooling is made to work mainly downstream from the code.
I have another question about selfing. So you mentioned that it's non-transitive, so the level of each component in the chain is independent. So if I'm writing code, can't I just extract all the non-compliant parts to a library, and then my own thing is self-fulfilling?
Yes, it would be. That's yeah. But the idea is that it should help you know where you're at, and if you want to lie, you can always say that you have a level 2, and that's really something that's first that's thought for self-improvement and not for proving something in the first place. So yes.
For the developer, we talk a lot about the dependencies. Are we doing something for the team? Because at the beginning of this year, there was some articles about the full extension of the marketplace for one point, how you can attack that with this type of
Yes.
kind of attack. And I learned already somehow sometimes some developers have like 200 extensions in their district. How are you addressing that?
I don't know of a special initiative. That's part of the whole developer workstation black box that is also.
Someone's working on that because I searched on the internet. No one is talking about how to secure a developer.
I'm not aware of initiatives in this regard. Okay, so a bit late. I think if you have questions, you can send them to me, and we'll switch to the next talk.